All right, here we go. Section 8.3, the converse of the Pythagorean theorem. So the Pythagorean theorem tells us that if you have a right triangle, then if C is the hypotenuse and A and B are the legs, that A squared plus B squared equals C squared. So the converse turns that around. The Pythagorean theorem converse. If the square of one side of a triangle is equal to the sum of the squares of the other two sides, then the triangle is a right triangle. Just literally flipping that thing around, which is what the converse, of course, does. So in other words, if A squared plus B squared equals C squared, then it's a right triangle. That is what the converse of the Pythagorean theorem is. It's just going the other way around. We know that we have a right triangle now. Remember this, C is always the biggest side. Always. So, first set of questions that you'll have, like here in this example 1, if a triangle is formed with sides having the lengths of that follows, is it a right triangle? So what you need to do is first identify the biggest side. That's your C. The other two are your A's and your B's. It doesn't matter if A is bigger than B or B is bigger than C. Or sorry, A is bigger than B or B is bigger than A. All that matters is that C is the biggest. So throw that into the formula. 16 squared plus 30 squared. Does that equal 34 squared? Yes, it does. 1156 equals 1156. So yes, that is a right triangle. For part B over here, we'll identify that C is 6. That's the biggest side. So does 3 squared plus 4 squared equal 6 squared? 9 plus 16 does not equal 36. So no, that is not a right triangle. Question C over here says, if we have two sides, this one looks a little bit different. We have two, the biggest side is 7 or 7. Well, let's choose this one of the 7s. Does 1 squared plus 7 squared equal 7 squared? Something feels a little funny on this one. No, 50 does not equal 49. How could the longest side, anyway, no, that's not going to work. If there is no longest side to a triangle, guess what? It's not a right triangle. There is no isosceles triangle that's a right triangle. So give these 4 down here a shot. I'll come back and help you with number 3 here in just a minute, but I bet you can figure them out. Give it a shot. Pause the video. Did you get no yes, no yes? Hope so. Number 3 was a little bit different, though. Let me talk to you about it. Square root of 5 is bigger than 2 and the square root of 2. So the way this works is you go the square root of 2 squared plus 2 squared. Does it equal the square root of 5 squared? What you just need to remember here is that the square root of 2 squared is like square root of 2 times the square root of 2, which we've learned is equal to 2. The square root of 5 times the square root of 5, that's the square root of 5 squared is equal to 5. So does 2 plus 4 equal 5? Well, of course not. Oh, I just spilled coffee all over my shirt while y'all were practicing those, so sorry about that. Big stain over here. Anyway, now there are several very common combinations, and we call these Pythagorean triples. These are ones that you're going to want to be on the lookout for. You will learn these and see them again. The first one here is a 3, 4, 5. We call it a 3, 4, 5 right triangle because 3 squared plus 4 squared equals 5 squared. So it becomes a common triple. Anytime you have 3, 4, and 5, you know it's a right triangle. We can use that 3, 4, and 5 to come up with bigger triangles, similar triangles. We use that as a ratio, 3, 4, and 5. If we multiply those by 2, we get 6, 8, and 10. If we multiply it by 3, we get 9, 12, and 15. So if the 3 sides of a triangle are 9, 12, and 15, it's a right triangle. It has the same ratio. We're just multiplying the 3, 4, and 5 by the same numbers. Times 4 is 12, 15, 20. 5 is, times 5 gets you 15, 20, 25, etc., etc. We all have the ratio of 3, 4 to 5. So if you can reduce the sides of a triangle to a 3, 4, 5 triangle, you know it's a right triangle. It's a common one. 5, 12, 13, same thing. 5 squared plus 12 squared, that's 25 plus 144, equals 169. 5, 12, 13 is a very common right triangle, so you should learn it. So if 5, 12, and 13 is 1, so is, if you multiply times 2, 10, 24, and 36. Times 3, 15, 36, 39, 20, 48, 52, etc., etc., etc. You can keep going with that, but the common piece of this is the ratio of those three angles is 5 to 12 to 13. I bet you can fill in these other blanks over here. See if you can. Did you come up with these numbers? By multiplying by 2, and then or by 3, or by 4. Try the same over there with the other common Pythagorean triple, 7, 24, 25. These ratios here, I don't suggest that you memorize like every single one of these, but the 3, 4, 5, 5, 12, 13, 8, 15, 17, and then 7, 24, 25, yeah, you need to be familiar with those. We'll talk much more about that in the near future. So here's how this gets started. By the way, you'll use this in future math classes on the SAT, the ACT. They love these special right triangles and not the special right triangles, the Pythagorean triples. But here's an example of how we can use the Pythagorean triples. 14, 48, and what? We could use the Pythagorean theorem, but it's just simpler this way. Check this out. If we have 14, 48, and blank, of course, x is the hypotenuse, it's the long side. But if we reduce the ratio of 14 to 48, if we reduce that, you get 7 to 24. Well, flip your page over. Do we have one where the two legs are 7, 24? That would make the hypotenuse what? 25. Well, the ratio we had was times 2. So 7, 24, 25. In this case, it's a 14, 48, 50 triangles. X equals 50. So see if you can reduce those other ratios on numbers 6, 7, and 8 and figure out what X is. Hopefully you got these answers. Okay, the final piece of this puzzle is that there's three theorems. They're totally related. We're going to learn them all at the same time. Theorems that determine right, obtuse, or acute triangles from lengths of sides. If you're listening right now, underneath where it says theorems that determine right, obtuse, or acute triangles, right, left, or wrong triangles. I'll know if you were paying attention. So, here's how this works. For each of the following, let C be the longest side of the triangle. We've been saying that over and over again, and that's key. So by comparing C squared to A squared plus B squared, we can determine whether a triangle is obtuse or acute. Okay, so the first one here, in no particular order, just the order I've done them in, if C squared is greater than A squared plus B squared, then is it a right triangle? Well, of course not. We learned on the previous page that if there's equal, they'd have to be a right triangle. It's an obtuse triangle. If C squared is greater, it's an obtuse triangle. So if I draw a triangle and label these sides A, B, and C like this, when you use this notation, angle A is always opposite side A. Angle B is always opposite side B. And angle C is always opposite big C. We use big, or the side C. We use capital A, B, and C for the angles, little a, B, and C for the sides. So in this case, angle C is an obtuse angle, and that's an obtuse triangle. Why? Because C squared is greater than A squared plus B squared. That's how we can know it. So what happens if C squared is equal to A squared plus B squared? Well, this is what we learned before. That's a right triangle. So if we draw the same type of triangle here with A, B, and C, where is the right angle? Well, angle C is the right angle, always opposite the hypotenuse. So we've talked about C is greater than A squared plus B squared. What about an equal? If it's less than, then the triangle is, you probably can deduce what goes in there. It's acute. So what happens here? Angle C is an acute triangle. So by comparing the biggest side squared versus the sum of the other side squares, you can know what type of triangle that you have. So example 2 down here. If we have these three sides, 8, 12, and 13, the biggest side, of course, is C, so we need to compare 8 squared plus 12 squared. How does it compare to 13 squared? Well, 64 plus 144 is greater than 169. Oh, settle down there. It's greater than. Now, you have to pay close attention here. Did I do C squared compared to A squared plus B squared, or did I do A plus B squared compared to C squared? I got A plus B over here. This is C squared. So C squared is actually less than A squared plus B squared. Remember, like the shark eating the bigger number, or the alligator, or whatever. But that is an acute triangle because C squared is less than A squared plus B squared. I'll do it both ways here on number B. The hypotenuse, of course, is 7. I said something wrong earlier, I just realized. You can't have an isosceles triangle with a hypotenuse and one of the legs being the same side, the same length. That is the thing that doesn't work, so sorry about that. Here in this one, we get 4 squared plus 4 squared. How does that compare to 7 squared? Or we could flip it around and say, how does 7 squared compare to 4 squared plus 4 squared? It's the same relationship, but it's a matter of which way you're going to go. You just got to pay attention. My C squared is right here. C squared is bigger than the A squared plus B squared. So what does that make it? What type of triangle? That's obtuse. If it's 4, 5, and 6, 4 squared is 16 plus 25. How does that compare to 36 squared? 41 is greater than 36, or C squared is less than A squared plus B squared. So it is acute. Okay, I'd like for you to try this set of questions 9 through 16, but before we do, I'm going to help you with number 13. It's got the radical in it. Just want to make sure you're thinking about what that means. You may want to use your calculator and determine, is 4 bigger than 2 squared root of 3? And it is. So to compare this, is 2 squared plus 2 squared root of 3 squared. How does it compare to 4 squared? Well, you know how to do this. We're going to square the 2, which is 4. And then to square this is like having 2 squared root of 3 times 2 squared root of 3. 2 times 2 is 4, times, what's the square root of 3 times the square root of 3? 3. So it ends up being 4 plus 4 times 3. 2 times 2 is 4, square root of 3 times square root of 3 is 3. And how does that compare to 16? Well, they're equal, so that's a right triangle. Didn't mean for you to see all of those answers. You got me. Give those a shot, please. Okay, hopefully you did well on those. Of course, if not, we'll go over them in class. These last 4, if you've already spent a long time doing this and you're frustrated, we'll talk about them later. But if you're filling up for it, give these a shot. I'd encourage you to. Let me give you some hints on these. We're trying to figure out, are any of these triangles right triangles? Don't forget that there's 3 triangles right here. The 16, 17, 17, the 16, the 30, and the 34, and then the 17, the 17, and the 30. So use those 3 sets of numbers to determine if there's right triangles. On the next one, we have diagonals that are bisected. So what shape do we have? Yeah, that's right. Thanks, Sarah. That's a parallelogram. So that tells us some things. Oh, look. 5, 12, 13. That tells us. I've seen those numbers before. Okay, anyway. 5, 12, and 13. Oh, and that's 5 and that's 12. And I bet that's just, okay. Give those a shot and see how you do. I'll display the answers in just a second. All right. Hopefully you did well. If you have questions, be prepared to ask them. and get a good night's sleep. There's a lot going on these days. Bye.